So, hello everyone. Thank you very much for coming to my talk. The organizers asked me to talk about my new neutrino mass constraints from the eBOSS Lyman-α forest. So this is a picture of me. This is work done in collaboration with my graduate students, all of whom are listed here. And two of them have already graduated, and the third will graduate soon. So also these are the archive numbers here so far from this work, so you can look it up after the talk. So just as an introduction, what is the Lyman-α forest? So the Lyman-α forest is one of the classic probes of small-scale cosmology. It comes from the absorption from neutral hydrogen in quasar sight lines, and its specific use is that it traces the dark matter potential well at high redshift. So the neutral hydrogen is clustering in regions of dark matter potential, and where there are overdense regions of dark matter, there will be more absorption in Lyman-α in the quasar spectrum. And you can use this, you can find the power spectrum of this to measure structure. So for example, here I've shown a sight line running through some gas density. The overdense regions are shown in bright red here. Where we go through an overdensity, so for example here, there is an absorption trough right there. Another one here corresponding to this one. Right? And the nice thing about this is it measures structure on small scales and high redshifts where there aren't that many other probes. So why is this useful for neutrino mass? So this is useful for neutrino mass because we measure a specific set of scales here, shown in gray, which are not accessible otherwise. And we measure the amplitude of the power spectrum on these scales. We measure, for example, something like sigma 8 on these scales. And you can compare that to the measurement of sigma 8 measured by the CMB on larger scales. And if there is a neutrino mass, the Lyman-α forest will have a lower sigma 8 than the CMB. Because the neutrinos suppress the growth of structure on small scales. So on its own, the Lyman-α forest does not measure neutrino mass at all. The generosity with sigma 8 is complete. But once you combine it with another measurement on larger scales, the constraints can be actually really tight. So just to show you a little bit about what we're measuring. So this is the 1D power along the line of sight to the quasar, and then averaged over all the quasar sight lines in the sample. We are measuring it in velocity units because we're a redshift space measurement. And so there's this factor of h of z in the units. To convert between the units that I'm showing here, so for example, this is eBOSS between k of 10 to the minus 3 seconds per kilometer and k of 0.02 seconds per kilometer, you basically multiply by 100, redshift 3. So this is 0.1 h per megaparsec to 2 h per megaparsec. So these are very small scales. Importantly, because they are small scales, they are non-linear, and we must have a simulation suite to analyze this data. I am not the first one. We're not the first ones to do this analysis. So the last analysis from the eBOSS collaboration is this archive number, which I'm going to call PD 2020 from now on. And they found that they measured NS and sigma 8, NS being the spectral index of the power spectrum, and sigma 8 being the amplitude of structure on 8 megaparsec scales. And they found NS of 0.954 and sigma 8 of 0.826. By comparison, Planck has NS of 0.965 and sigma 8 of 0.811. So these are the tightest neutrino. These measurements, because they are quite precise, they lead to the tightest claimed neutrino mass constraint. This is mu, the total mass of neutrinos, less than about 0.11 eV. So that's quite tight. And the reason that's interesting, especially, is that it rules out the inverted mass hierarchy, which requires a total neutrino mass greater than 0.1 eV. These constraints, because these are in combination with Planck, they are driven by the high sigma 8. Right, so you'll notice that the measurement of sigma 8 from PD 2020 is a little bit higher than the one from Planck, and that is making the constraints tighter because there's no room to reduce the power on small scales if you're measuring at a higher power within the. So why did I want to do a new analysis? So I was really motivated by the upcoming Lyman-α forest sample from DESI. So this is going to have a lot more quasars. It's going to have much better statistical and systematic error, especially at high redshift. And the earlier simulations, the simulations used for the earlier analysis are about 10 years old now. And they were not enough to model all scales. So what they did was they had a large box, low resolution simulation, and then they matched it together with a small box, high resolution simulation. And the correction factor between the two was modeled with a nuisance parameter analysis, which they analyzed over. So we have the opportunity, due to advances in simulation technology, to run bigger simulations with better models and avoid doing this, right? So we have one large simulation suite, which is enough to model all the relevant scales. Here is a video of my simulation suite. This is the PRIYA simulation suite, named after my wife. And here is a sight line running through the simulation box. There's the box boundary, running through the simulation box and running through the gas density limit. And thanks to my student Lyman-α for this video. So a little bit more about the suite. So this is a suite of 50 full galaxy physics simulations. The resolution is about the same as the illustrious 100. There are 50 of them. Each of them has a different set of cosmological parameters, and they run to redshift 2. So this is quite a large simulation suite, just to be clear. Here are some of the parameters. So the maximum particle load for the full resolution boxes is 3072 cubed. And they are in 120 megaparsec boxes. They have a 40 kiloparsec mean spacing and a 1.3 kiloparsec softening. So that's similar, but a little bit better actually than illustrious 100. And they use the full galaxy physics model from the Astra simulation, which has been shown to do well on various galaxy formation problems. So we also have, importantly for Lyman-α forest, we also have patchy hydrogen and helium reionization models. Our patchy hydrogen model allows us to model the fact that the temperature of the gas is different at different parts of the box. And this is important because our boxes are larger than everyone else's, right? So our boxes are for the first time order of 120 megaparsecs. And this means that we can model the different patches. Patches are smaller than that. The helium reionization model, which is quite novel, is modeled with a bunch of patches of 30 megaparsec bubbles that are placed at random around quasars, around randomly chosen quasars, between redshift 3.8 and redshift 2.8 when helium ionization finishes. The parameters of helium ionization, so the start and end redshift and the heating during helium ionization, are varied in the suite and marginalized out in the final analysis. So once we have this simulation suite varying various parameters, we use it to build an emulator for Lyman-α forest. The purpose of the emulator is to predict the flux power spectrum for an arbitrary set of parameters. In particular, we want to predict the cosmological parameters. And what I've done is to parameterize the power spectrum with these two parameters, AP and MP, which are analogous to the standard CMB parameters AS and NS. So NS being the spectral slope and AP being the amplitude of scalar perturbations, but they are on much smaller scales. So the pivot scale here is 0.78 H per megaparsec, whereas the CMB usually uses 0.05 H per megaparsec. And notice that if there's no running in your model, if alpha is 0, then NS and MP are the same. I just use MP to make it clear that we are technically measuring a different scale. We also have washed off for the purposes of this conference, nuisance parameters for the properties of hydrogen and helium reionization. And we have an important nuisance parameter called tau naught, which is the mean optical depth of Lyman-α forest. This is analogous to the galaxy bias in a galaxy bias model. It is necessary because it encodes the ionization fraction of the neutral hydrogen gas. And we need to encode that because we don't know the amplitude of the ionizing background at redshift 2 to sufficient precision for this analysis. So we need a nuisance parameter. So that was a quick, very quick introduction to our pipelines. You can look at the papers for the full details. Let me now transition to talking about the results. So here are some chains. I have shown you two different sets of chains, both in the flux power spectrum using different redshift ranges. So these are the cosmological parameters. The gold is the full redshift range available to eBOSS, redshift 2.2 to 4.6. And the blue is a reduced redshift range from redshift 2.6 and 4.6. And the red is a similar chain which also incorporates some information from small scales on the mean temperature of the IGN, which is not fully independent. So the most conservative thing to do is to look at the blue chain, which is what I'm going to be doing the rest of the blue or gold chain, which is what I'm going to be doing the rest of it. So one thing you will notice is that the gold chain, which uses all of the data available, has a very low spectral index and a moderately low scalar power spectrum amplitude. Whereas the chain with the reduced redshift does not. NS is much higher, MP is much higher, and AP is moderately higher. So this is interesting. This low MP with the full redshift range is driven by an internal tension, it turns out. So it's driven by a tension between the data at redshift 2.2 and redshift 2.4 and the data at higher redshifts. And I've plotted here the best fit power spectra at some important redshifts. And you can see that here is the redshift 2.2 data, this black line here. Here is the redshift 2.4 data, this black line here. And the gold line is the best fit to the model fitting everything. And the red line and the black line and the blue lines are the fits to the model with the reduced redshift range. And you can see that none of the models, even the ones trying to fit to the redshift 2.2 data, are actually a particularly good fit, right? Like they're all pretty discrepant, I would say. So that is what we mean by an internal tension, right? I mean, these data sets are not internally consistent. So there are two things to be going on here. One of them is that there could be something that's not included in the theoretical model. So in particular, if AGM feedback were doing something unusual at redshift 2.4, if there was a very strong amount of AGM feedback, then that was not included in my simulation model, then that could be upsetting the chains. Another thing is that there's simply some sort of data systematic at low redshifts in the eBOSS data, and we should throw away these redshift bits. It turns out that the early data release DESI data does not agree with eBOSS data in the redshift 2.2 and redshift 2.4 bins. So this is at redshift 2.2. The red is the DESI early data release data, and the black is the SDSS data. And you can see that they're discrepant within their error, but they're discrepant by more than their error bars, right? So they don't agree. So there's clearly some data systematic somewhere. This to me, and at redshift 2.6, the agreement is much better. It's consistent within the error bars. So this to me suggests that this is most likely a data systematic, that something is happening at redshift 2.2. In the DESI paper, they suggest that about half of this could be due to continuum fitting. Sorry, about a third of this could be due to continuum fitting or the DLA models, and the rest is unaccounted for. But clearly there's something going on here. The most conservative thing to do is to throw out the data at redshift less than 2.6 and look only at the change in reduced redshift range. And that is what I'm about to do. So with the restricted redshift, redshift greater than 2.6, now we're looking at the blue and red contours here. We find that MP is greater than about 0.969. There's no upper limit because we hit the prior volume of the emulator, but it would be about 1.02, I would say. And sigma 8 is 0.733 plus or minus 0.026. I also want to say one thing about the bias parameter that we had at the beginning, tau naught. This comes out to be 1.098 plus or minus 0.02. This is a unit that is scaled against a fiducial model, which is that of Kim et al., which would be 1.0. So these measurements are actually consistent. So this tau naught measurement is consistent with earlier data sets from different quasars. Becker et al. Found 1.1 plus or minus 0.01, which is the same as what we find. And Kim 2008 found 1.0 with a complete distinct data set, but the error bars were quite large. So this is consistent. So that's a reassuring thing. Our galaxy bias model is the same as other methods. How does this compare to Planck? So Planck finds NS of 0.965 plus or minus 0.004, and our NP is consistent with that at about 1 sigma level, which is great. Notice that the earlier measurements from PD 2020 were discrepant, and that discrepancy has gone away. Interestingly, because our models do allow for a higher MP, in particular MP1, we can't rule out the Lyman-α forest cannot be used to rule out early dark energy models, which is fun. We've also looked at sigma rate. So my eBOSS measurements have a sigma rate of 0.733. That comes from this parameter here from AP. This is lower than Planck, right? So Planck comes out as sigma rate of 0.811. So we are roughly 3 sigma lower than Planck. So in some sense, we've taken a discrepancy with the scalar, with slope, and transformed it into a discrepancy between the power spectrum amplitude. Planck is not the only measurement of sigma rate. We can also compare to other small-scale measurements of sigma rate, in particular the dark energy survey, and that gives 0.733 plus or minus 0.04. So this is great, right? Okay, so we have agreement. Wonderful. I mean, it's obviously a coincidence that we agree this well, right? I mean, I agree perfectly. The error bars are larger than that, but we do agree within the error bars. So I have, this is a measurement of, one way of looking at this is the measurement of the S8 tension even at redshift 2 to 3, right? So we've measured sigma 8 at high redshift, and we get the same measurement that there's also at low redshift. So this is an independent confirmation to dark energy survey in some sense. I have deliberately not run joint chains. However, we can draw some conclusions for the neutrino mass. So in particular, I told you the neutrino mass comes from measuring large-scale CMB scales, sigma rate on large scales and sigma rate on small Lyman-α scales. And we're finding sigma rate on Lyman-α scales to be about 8% lower than the CMB. The best fit to this, as shown in this wonderful plot from Chris Pedersen's paper in 2019, which is the purple lines at redshift 2 and the red lines at redshift 3. So a reasonable fit will be about a neutrino mass of about 0.3 eV. Notice that with the error bars, we are maybe 3 sigma less than, right? So once various things are marginalized over, this is going to be a less than 3 sigma evidence for a non-zero neutrino mass. So this is not, I deliberately have not run the chains because I want to make a few more checks before I really make this claim. However, this is somewhat intriguing. It could still be statistical, but it will be interesting to see what DESI comes up with and whether whether this is still the case. I do think that the former tight constraints for Lyman-α forest of mu being less than 0.11 eV have been overturned. And I look forward to the full DESI power spectrum to see what results that gives. So thank you very much for listening to me.